such 2D structures when applied to aerospace vehicles in particular, and what is the nomenclature that is typically used in the industry for those different components. Similarly for the beam-like structures also, where it is used and what functions they perform and what names they have. So that's essentially the way in which we will go forward. So this is what, based on all of your inputs, we summarized last time. The reason why we need shells and beams, the answer to that, one, of course, we started off saying the obvious reasons, that is the weight considerations, some production considerations, etc. In addition to that, we talked about structural considerations, aerodynamic considerations, and then from the functional point of view, what is the functional consideration? So the functional consideration, let's start with that. It's quite clear that when you have a vehicle, the whole idea is to transport certain payload from point A to point B, maybe bring it back also, but what you're talking about is essentially a transport. So that has to go into the vehicle, primarily because the kind of atmosphere that we fly in, because you would see probably in mythology and things like that, some people are sitting over a vehicle. That is another possibility. But that's okay as long as you're traveling in atmospheres which are of conducive temperatures, pressures, etc. Here you're traveling at a very high altitude, which is at very low temperature, very low pressure. So obviously you can't be outside the vehicle. And also you're traveling at a fairly large speed, and the drag matters. So you could be a cause of a huge amount of the drag as well as payload. So the whole idea is very, very obvious from all these functional aspects that you want to put them in. And not only when we talk of the environment, one is the low pressures and the low temperatures, but the other aspect is also the low levels of oxygen. So that's again very well known even to mountaineers when they climb very tall mountains. They need to carry their own oxygen because the oxygen levels can go down quite a bit with altitude. So obviously that's taken care of, as was pointed out by the officer, in terms of the regulators, how you release the air, and still you maintain that typical fraction of oxygen in the air at the ground level while you are in the higher altitude as well. So that is one thing from a point of view of protecting the payloads. The other is also, some of you gave examples of what other kind of contents could be there. Fuel, for example, has to be inside. So that has to be protected as well in some sense. And then the control links, whether it is hydraulic, pneumatic, or fly-by-wire electric systems, all those connectivity from where the pilot operates the controls to eventually the control surfaces, all those mechanisms and links that are there, or the cables carrying the electrical signals in fly-by-wire systems, you need to have room for that, and that again needs some kind of protection. The avionics needs certain protection. It also operates optimally for a longer life period only when it is within certain conducive temperatures and pressures, etc. So all of that needs protection. So that's purely from the functional point of view. You will see that you want to have the material as far outside as possible. The overall shape and sizing has been done by the aerodynamicist in terms of how the wing should be to generate a certain amount of lift. We also saw that typically you can consider it as a beam. Very obviously the wing and also the horizontal and vertical tail can be considered as cantilever beams, whereas the fuselage can be considered as a simply supported beam with some kind of an overhang. It's very simple to see that, let's say you consider this as the fuselage. If you look at it, essentially what you're saying is the large amount of lift is generated by the wing. So the wing is almost like carrying this beam. And then there is a small amount that is offered by the tail, and depending upon their relative position with respect to the CG, sometimes this could be positive or sometimes this could be negative in order to maintain that kind of stability that you want to have. So essentially, more than simply supported the way we understand from typical beams at the bottom here, essentially those the empennage, in particular the horizontal stabilizer, and the wing they are essentially balancing this whole thing. And so this is essentially a long structure, has some level of overhangs, which also could have certain levels of stress. So you need to address all of those aspects from the beam perspective for the overall aircraft for a very preliminary analysis. And then you go into the actual structural components. Each of them have their own shell or beam-like behavior, and then you try to look at it. Some time back I was talking about damage mechanics, where you do a substructure analysis. This is also kind of a superstructure that you have, which is the wing and the fuselage, and then you boil down to the actual shells beam components, which are the structure, and then when you want to do a damage analysis, you go to a substructure. So superstructure, structure, and your substructure is the direction in which you flow. From the aerodynamic aspects, we already saw that a certain airfoil cross-section needs to be done. The earlier stages we had just low subsonic flights, a very thin airfoil cross-section, typically with a positive camber, was used for the wing, and then they slowly started going to higher and higher speeds. You essentially subsonic still. You're talking about a flat lower surface for the airfoil, and then a curvature on the top. So essentially you're talking about having the low pressures or high velocities on the top, so that you're essentially generating a resultant force which is upwards, which is essentially your lift force perpendicular to the zero lift line. So this kind of necessity also means that you are trying to give that outer shape, and when you're giving the outer shape, you cannot have a very flimsy skin, so you obviously have to have some minimum material that is required in order to give you that shape. And in fact, some of the structures that we will see inside is a very simple box beam that you see over here, because it actually goes much longer. It's just one section of the wing which is cut over here. Could go much in front of the screen as well as behind it. So that length, you're essentially talking about a beam-like structure over there. In addition, there will be what are known as transfer stiffeners. We'll go to specific names for them, whether they are in the wing or the fuselage, etc. And those are, many of them are typically coming from the biological connotation. You have a backbone, which is your primary bone, and that is typically, like in the case of a wing, it is a spar. And then you have at different locations, you have the ribs, so which are essentially transverse stiffeners. So, and again, the skin. So typically, you're talking about purely from biological perspective. Of course, there are other components which may not have a direct correlation in terms of how they are named with what we have in the body, but essentially the ideology or the way in which we bring about the requirements, satisfy the requirements, is to a large extent influenced by biology and taken further in terms of making it much more efficient for the kind of specific needs that we have here at much larger speeds, higher altitudes, etc. And this is something not unique to just vehicular structures which need to translate payload. Even a civilian structure like this, it needs to house people. So that's why you see so much of a hollow space inside. Otherwise, you build the entire structure without any gap in between. There's absolutely no point in it. It could be a memorial, for example. But if you want it in a functional sense, you obviously need to have the space for that. And then instead of aerodynamics, you typically have some aesthetics going on to the outer shaping. And in the case of a submarine or, let's say, a ship, the hydrodynamic aspects come into picture. So all of them typically will tell you to move the material out. And the first one, which is the most important for us from this class's perspective, is the flight vehicle structures perspective, the structural perspective. We saw that for the typical kind of cross sections which are used for beams, for spars, for example, you typically have like an I section and this I section. You could have, instead of having it in this particular way, you could probably think of it what we call as the web over here. Suppose you cut this and put it into a horizontal kind of a thing, and you have a rectangular solid cross section over here. So this is that web that was there. You essentially putting it like this. So you can see that, for example, let's, even though I am not drawn to that scale, let's say this is height by 3, the height by 3, the thickness of this is also h by 3, so that you have a total of h over here when you stack them all together, and let's say they have a breadth of b. The h is typically very small compared to b, but so it doesn't matter whether you're going from the center line or from the edges or whatever. So you're essentially saying this is your breadth b. Now you can very easily verify from your basic high school mathematics that the moment of inertia about, let's say, the center line over here and the center line over here would be very, very different. So this is going to have a much larger I, which is the moment of inertia about this particular axis. Let's say, let's call this as y, let us say, and this as z. So essentially about the y-axis you have, so what you call as the second moment of inertia about the y-axis. Similarly, over here, once again, you have the y and z. So about the y-axis is what you're essentially talking about. So you would see that the I y for the I section would be much larger compared to the one for the rectangular cross section. But the area is the same. Both of them, if you take up the total area of the cross section, it is equal to the breadth times the height, BH. So in spite of both of them having the same cross-sectional area, which means the same amount of material, if you're looking at the length of the beam, same in both the cases, which is what it is. For example, if it's the spar of a wing, you're talking of how the semi-span, or at least if it's running all through, but otherwise you'll have to reduce half the fuselage diameter in order to arrive at the overall length, or it may not run all the way to the tip where the stresses are much smaller, so you might curtail it at some extent just before the wing tip. So depending on all of that, you would have a slight difference, but essentially you're talking of the same spar. The spar length is going to be same, of the order of magnitude of the semi-span, and in spite of having the same amount of material, which means the same mass, one is going to be performing much better in bending compared to the other, assuming that you're using the same material for both, let's say an isotropic material, aluminum alloy or whatever. So you're essentially talking about one's bending stiffness being much larger than the other. So for the same applied load, which is, let's say, both the aircraft are flying under same conditions, it's generating a certain lift with a certain lift distribution, approximately, let's say, elliptic. So both the loading cases are the same. The cross-sectional area, the mass is the same, but one is performing much better than the other in the sense that the curvatures that develop, which is essentially a measure of the deflection, so is going to be much lesser in the I section compared to the rectangular cross section. And the same thing, you can, instead of having it like this, I can cut this whole thing and put it up into a circular tube kind of a cross section. Assuming all these are sheet metals, let us say, you can curve it and weld it at some location. So essentially you're talking about this. This, let's say, has a radius, mean radius of R0. So the total length that you have is R0, let's say thickness T. So the area is approximately, if T is very small compared to the R0, then you would see that this is the cross-sectional area, which is once again the same as what you have over here. So I can work out R0 and T in such a way that it's equal to BH. So I'm essentially from the same amount of material, in other words, the same mass of the structure for the spar, I'm, let's say, making a tubular beam like this. Obviously, compared to either of these, you would have much larger torsional stiffness in this case. So the GJ that you would have over here, of course, in this simple case where you have a circular cross-section, J becomes just the polar moment of inertia. but for all other cross sections, it will have to be calculated in a different way. We'll look at some aspects of that a little later on. But essentially what you're talking about is GJ for the circular case would be much larger than your GJ for the other two cases, which is either the rectangular or the I section that you have. So what all of this is pointing out is this ability to transmit and or resist the loads which are applied to the vehicle, which come in the form of bending, come in the form of torsion, etc., is much better when you're trying to push the material out. And when you push the material out like this, it's obvious that you are able to contain something within that. So that could be the payload and or, so for example, if it's a fuselage, then you could probably have floor panel over there. The cargo could go at the bottom, the payload could go on the top, etc. So many different ways of arriving at the layout become possible once you have moved out. So from a functional perspective, it helps, and from the structural perspective, because your GJ is going to be much larger, that really helps. So in this case, of course, when the bending is the more dominant, you can't go for that. That will also have larger bending stiffness compared to probably a rectangular cross section like this, but this would be much superior in terms of the bending stiffness. So this EI would be probably large compared to even the circular cross section. Not as large as compared to the rectangular cross section. So you would have the circular cross section somewhere in between the two. But in terms of probably the more optimal sense for bending, you would probably look at it this way. But recollect that this airfoil is not only undergoing lift distribution, but also drag distribution, which means that it is bending in the other direction as well. But if you look at it from the neutral axis, there's a lot of material which is spread much further apart, and your moment of inertia about the z-axis, using the same coordinate system that we have over there, about the z-axis is going to be already quite big, and also your L by D is going to be bigger than 1, so your drag is not as big a load as your lift, and therefore both from the ability of the structural material distribution, your I's are more and therefore EI's are more, and the corresponding load that is coming, which is the drag, the bending moment due to the drag, is going to be much smaller compared to the bending moment due to the lift distribution that you have. In addition, of course, you're going to have the pitching moment, and also the not only the pitching moment coming from the aerodynamics, but also there's some moments that might come due to the way the engine is attached. So due to its weight and the thrust, these can be off from the so-called center. In this case, it's quite obvious that whatever center we are talking about is essentially the geometric center. But when we go to more and more these are also symmetric, doubly symmetric cross sections. So whether you're talking of the neutral axis, center of twist, shear center, etc., all of those will essentially be here. But when you go for asymmetric cross sections like what you have over here, which is a typical wing cross section that you have, then you need to have a non-trivial way of calculating those things, and each one of them can be different from the other in general. So we need to make sure that we are taking care of those aspects as well. So the pitching moment and all of these torques coming from the weight of the attachments, and also from, let's say, the control surfaces which are deflected at some phase of the flight, all of that is going to cause torques over here, and those torques have to be resisted as well, and which is why you probably need combinations of these kind of sections. As far as this is to take care of the lift distribution. Drag, as I said, it's spread out much farther, and the value of the load itself is small, so you probably don't need an I section which is turned around 90 degrees like this. That itself is usually good enough. And many large aircraft will have not just a single spar like this. The airfoil cord will be so large that you will have a front spar and a rear spar, maybe more than that also for much larger aircraft. So those are also going to offer you, by their spread away from the neutral axis in the Y direction, they're going to offer you a much larger IZ and will be able to handle the drag distribution bending moments. So it's very clear, I hope, in terms of whether it is for transmitting or, I'll just come, transmitting or for resisting the loads, moving the material out is going to help you with the better response to the structure, to whatever loads are coming. Yes, please.
For the loading scenario, the component which you are designing, that's facing a biaxial bearing for lift,
Correct.
for drag,
Correct.
both the things.
Correct.
Okay, so if we talk about this I section or any section of the tube, will we consider the biaxial bearing as a combination of loading, or will first for lift distribution we'll find out the section, then we'll find out the another, I mean, case by case we will analyze that component, then add the things, or we'll draw the combinations, we'll find out the combinations?
Yeah. It's an excellent question because it's very, very important in terms of how the whole process works. So one is either you're talking of a design problem or an analysis problem. The design problem, you do not have all of this data all together. So you need to start with some kind of initial iteration based on typical case studies of similar aircraft, and then you try to optimize for your particular thing. But eventually it has to be done as a combination. So you can't consider the lift alone separately and the drag alone separately, the pitching moment alone separately, and design each component for that and then take it forward. Maybe for the initial cut analysis, you could do that to come at some kind of an initial sizing, which you can then optimize along with the combined loads, because only when you go into the combined loads, you would see the stress interactions. Because remember that whether it is the lift distribution stress or the drag distribution stress, both are, as far as the material is concerned, axial stresses in the x direction, where x is perpendicular to the yz plane. So you have in the x direction is what the stresses will be depending upon the direction. So effectively, because this lift is the dominant load, so you would see that the top will be under compression and the bottom will be under tension. But because of the drag, you would have some more thing which is essentially talking about like this. So in other words, in certain parts it could be a relief, certain parts of the flange it could be adding to what the lift is causing. So if you had designed it only for the lift, let's say, then maybe those portions will not be able to handle lift plus drag occurring simultaneously. So the sizing, the shaping, everything has to come like that. So one is in terms of the combined loads, it is necessary. Not even in detailed design, or beyond a certain point, even in preliminary design, you would have to consider all of them simultaneously. And it's not just in terms of the combined loads, but also combined structural components, because it's not just this structure alone, which is your entire wing, right? This is a spar of the wing. So this is going to take the load along with the skin, along with the other spar. If there is more spar, there are going to be what are known as stringers or longerons, etc. You're going to have that. Then you're going to have at different locations what are known as the transverse ribs. So you need to account for all of that, their spacing, etc. So all of the not only combined loads, but also combined structural components need to all be considered simultaneously in order to do that. And it's very common that not all of these materials, not all of these components will be made out of the same material. You might have many different choices for the material that you use for each one of them. For the skin, it could be a different material from the spar and the other stringers, etc. So you need to consider combined loads, combined components, combined materials. All of this has to be considered simultaneously, because remember that for efficient operation, you're pushing the limits. And when you're pushing the limits, there is a possibility that certain locations you can get into nonlinear kind of regimes. So if you try to do each of them separately and then try to add them up in some, even if it's done in a rigorous way, you might still not have a good enough result at the end, especially when you're looking at detailed, let's say, towards the end of your design process.
So one more thing, that if you look inside the wing, the stringers, the ribs, they are forming like a truss-like structure inside.
Very good, yeah.
So can we, the way how we solve the trusses, can we solve these problems?
Excellent question that. In fact, we will see shortly that typically you have three types of geometries that are there, or structural design paradigms. One is the truss-like, there's something called the monocoque and the semi-monocoque. So what you're talking about is a semi-monocoque, where you have the skin along with the all these stiffeners, could be spars, stringers, etc. So now when you have all of these combined, sorry, I forgot your question. Yeah. So the truss is one of the types of design paradigms, typically for smaller sized aircraft and for lower speed aircraft. So when we started going into higher speed and larger aircraft, which needed to carry more payload, obviously that was not an efficient thing, and we had to move to that, to the monocoque and semi-monocoque. We'll talk about that in terms of the logic in a little more detailed way. So essentially, whatever our understanding is coming from the truss-like structure. So your question is whether the semi-monocoque construction can be considered as a truss with a skin or anything else which is attached to it, right? So yes, there is a way in which you could do that, but with the catch that in a truss, typically an ideal truss, you're saying that each component should not undergo bending by itself. It should have only tension or compression. And where there is compression, there's a possibility of not only material failure, but also structural geometric failure in terms of elastic instabilities, but like buckling. So the spacing and the length, all those things become important as well. So as long as all of these members that you're considering in your semi-monocoque construction are dominant in their tensile or compressive, essentially axial load carrying, that if that is the major load there, and their contribution towards bending by itself, or let's say, again, see, for example, if you look at the spar, it's very clear that one part of this spar is undergoing compression, the other part is undergoing tension. So you can still consider this as a separate member of the truss, and this as a separate member of the truss, and they are connected in some fashion. So you could think of that. But this cannot be a member which is a part of a truss, because this is mainly going to take shear. And by definition, a truss element cannot take shear or bending or torsion, etc. They have to be under tension and or compression, right? So yes, there are certain carryovers in terms of how you understand truss analysis and how you can utilize this. And in terms of the overall structure also, from a layman's perspective, when you look at it, you look at actually, if you remove the skin, it's essentially the semi-monocoque construction also looks like a truss. But from a pure structural perspective, unless and until it satisfies that definition of a truss that it has only axial loads, you will not be able to do a truss analysis and get reasonably accurate results. Right? So apart from the fact that it needs to carry all of these loads, remember that these are not, components are not in isolation. They are attached to the other structures either through riveting, bolting, and adhesives, and therefore there needs to be a certain level of load path and the load transmission that has to take place. In fact, the entire load will be transmitted because you're talking about equilibrium of each one of these structural components. So if you're applying a force F here, you have to have that force F, and along with the moment, whatever is going to come, that has to be transferred to the next component which is attached over here, if it's the only component. But typically you'll have multiple components, and all of them have to be under equilibrium as a whole, as well as individually they have to be under equilibrium, which means that they are transmitting all the entire force from one to the other. But if they were rigid bodies, they would be transmitting almost the entire energy as well. But because each one of these are flexible bodies with a certain elasticity, they are going to undergo certain strains and therefore strain energy, and therefore a part of the strain energy of the overall work done by the external loads is going to be taken by one component before it transfers the rest of the energy to the next component that it is attached. So in that sense, the energy is kind of distributed, because the external load, remember that the spar or the, let's say, the tube, etc., may not be directly experiencing it. It is coming through the skin of the aircraft, and the skin in turn, whatever it is connected to, it has to transmit to that. But the concept of what we call as the stressed skin comes into picture, where the skin takes some part of the strain energy, only then transfers it to the other. But in the truss design that you're talking about, you might still have some coverings. Like, for example, olden aircraft used to have the truss structure, then there could be some fabric covering, for example. The fabric is not expected to take any of the stress. You have to design the truss itself to take care of all the loads that are coming. In reality, what might happen, there's small amounts of stress could be there in certain parts of the fabric, especially where it is under in tension, depending upon how it is attached and how much it is taut in terms of the attachment points. Keeping all that in mind, you should remember that these two aspects of the structural response are very important. One is the structural component deforms, which is what we call as the resistance that it offers, and therefore takes some part of the strain energy. But there is also a part that it is transmitting, because when you are going to analyze each one of these structural components individually, you need to know that load transfer path. You will start off with the skin, because you know from your aerodynamicist friends what is the load distribution that is coming. So you know how the skin is going to respond to that. But you also know that the boundary condition for that skin is going to be in terms of how it is attached to the interior structure, that is all these spars, etc. So then you try to analyze along with the external loads and these individual connectivity, giving you the appropriate boundary condition. In the initial set of analysis, you might be able to, let's say, idealize it by saying that it's a fixed condition, or it's some kind of a simply supported condition, etc. But as you go, you will have to make room for these joints also being flexible. So it's not just the structural components which are flexible. Might be more rigid compared to the others. So some certain components might be treated in initial cut analysis as rigid compared to something else. But eventually, you know that everything is flexible. Similarly, the joints are also flexible, and therefore the contact mechanics which goes into it, and the joint mechanics which goes into it, the actual mechanism of how the load transfer takes place through a rivet, how it takes place through an adhesive joint, etc. All those need to be brought in if you want a reasonably accurate analysis going forward. So I think this is quite clear, right? This summary. Right?
So the structure is not a truss, sir. You will not
No. If you do, you might get very rough cut results, which might give you some kind of an idea of how it's going to behave, but it could be quite off from the actual behavior of this structure. Right? Okay, so as I said, all three are asking you to push the material out, so which is a very strange situation in design, because usually the requirements are contradictory with each other, and you try to come at some kind of a in-between result in terms of the decision that you take on how you're going to put how far out or how far in. But here it's very clear that you want to push the material as far out as possible to the limits whatever your aerodynamicist friends have given you. So now, based on that fact and all the three pushing forces, as well as the weight considerations, etc., that we talked about earlier, which essentially are also actually translate to that. Why that weight consideration comes is because the structural consideration, because the structure has to hold a certain amount of stress in the different direction. It's a multi-directional, kind of stress that you're actually dealing with. So it has to be able to deal with. So a certain amount of material, not only its location, but the amount of quantity of material is also going to be dictated by that. Once the quantity of material is dictated, it's quite clear that the sizing and the quantity are dictated. The mass or the structural weight considerations are going to come from that, right? So the most efficient location for structural materials, be it in bending or torsion we saw there, is going to be the vehicle outer surface. But let's say you have a situation like the helicopter rotor blade where you have a dominant axial load. That is all that is being considered. Then it doesn't matter each one of these how it is going to be. You might as well go for a rectangular cross section like this, and you would see that a lot of flex beams of helicopter rotor blades, which is the essential skeletal structure inside the airfoil cross section that you have, that is in many cases you would see that it's just a rectangular kind of a cross section. So that is a very rare case where only the axial loads are going to be dominant. Again, if you look at some of the semi-monocoque constructions for the stringers and or longerons in certain aircraft, you may not go for these thin mulch sections like a hat or a channel or a T section, I section, etc. Some cases just a rod, which is a solid rod, could also be good enough, or a rectangular if the attachment point has to be proper to the skin. So therefore, the circular cross section, when you attach to the skin, the joint will not be strong enough. You typically go for, let's say, a flat plate kind of a thing, which is again something which is going into a rectangular kind of a cross section. And also in terms of the distribution, see, you're going from what is, let's say, just the skin alone to a situation where you have the skin along with this stiffening elements. The whole idea of going from one to the other, what we call from the monocoque to the semi-monocoque, is essentially more structural efficiency, because if you had let the monocoque kind of design continue for larger aircraft and or faster aircraft, then you would have ended up with a very, very thick skin, which is going to be very heavy in terms of the structural weight penalty that it's going to contribute. So the idea is that, let's say, instead of, if I wanted to design it and purely from a monocoque design, I arrive at some level of thickness T, then when I want to move to the semi-monocoque design, typically what is done is, instead of whatever is required as T, I take only half the T, and the remaining half T, I try to distribute it at various locations in the form of these stiffening members, and then I see that it's an over design, so I can remove some of these components. So essentially, you don't need that total amount of weight that you had as, let's say, to T to start with. Now you have just half T thickness skin that you're going to be dealing with. You can take this example itself. If it's, let's say, the fuselage over here, you started off with a thickness T that you had. Now you want to use the same aircraft at a higher speed or to take more payloads in larger aircraft, either one of them or both of these reasons, what happens is the stresses become large. So your T required will be very large. So instead of having just a geometry like this, instead of going for T, I take, if T had become very large, I will take just half the T, and the remaining half T, whatever material I save from that, I will start putting it as stiffening structures over here, joining it. And if I do that, I will eventually see that that is kind of over design. In other words, the stresses come down so drastically that it's much away from the failures of these materials, whether it's of the skin or of those reinforcing components, and therefore you would want to space them farther apart or size them smaller than what you had sized, or combinations of that, so that eventually you will see that the overall cross-sectional area and therefore the amount of material that you have, or the overall mass of the material, will come down. Your structural weight required will kind of come down. Okay. So now let's step back. Jumping ahead in terms of talking about the semi-monocoque design, the truss design, etc., based on some of the questions which came up. But let's go back and go through it in a logical sequence of arguments of why we need those three different design paradigms. So the most efficient location for the structural material has to be the vehicle outer surface based on those considerations. And therefore, it's very clear that once you push the material farther and farther out, you end up with a shell like this for the fuselage, which is either circular or some kind of an oval shape, or for the aerodynamic surfaces, be it the wing or the stabilizers, you would end up with an airfoil cross-section like this. But whether it is this airfoil cross-section or that circular or oval cross-section that you see over there, both are essentially shells because of the fact that their length and the width are much larger compared to the thickness. In that case also, you see the circumference of that is much larger compared to the thickness. R itself was large compared to T. 2 pi r times T is going to be even larger. And then the length, of course, of the fuselage is going to be much larger than the thickness. So one dimension, that is the thickness, is smaller than the other dimension, which is the circumference and the length, other two dimensions. Similarly, here also the thickness of the airfoil is small compared to its chord and the semi-span, and therefore in both cases it qualifies as a what we call as a shell, essentially a two-dimensional material. In other words, for your mathematical modeling purpose, even though it's in reality a 3D structure, you can treat it as a 2D structure. And if you have the theory derived properly and implemented in the algorithm and eventually the computational code, then the kind of inputs that you give it are also appropriate, then you would get almost same accuracy with doing a 2D analysis as you would do with a 3D analysis for this. And of course, you would save a lot of computational time through that whole process. Within the shell, yeah.
If you do 2D analysis here, then you are approximating the thickness part.
Correct.
Then how we will decide that what will be the thickness of that? I mean,
Yeah.
if you designing arbitrarily, it might go over.
Very good question. Very good question. Okay, so right now let's not talk about that, but an equivalent answer I can give you from a beam perspective. Okay, so now in the beam perspective, what you're talking about, once you've defined your moment of inertia and therefore the bending stiffness as this, I can just treat this as a one-dimensional structure of a reference line, or if it's a curved beam, let's say a reference curve, and I can do the analysis. But what I'm doing essentially by using this quantity is that I have analyzed the actual cross-section already and lumped all of these properties to that particular point in the cross-section. Then there's a loci of those points along different cross-sections, which forms your reference line or reference curve. And then I can just treat that as a 1D analysis. So where that information has gone is it's getting lumped into this, or in a torsion problem, it's getting lumped into this.
Basically, we are using pure bending of your torsion equation while converting that EI from when you are treating that beam in a line.
Yeah.
Then we are using those.
Correct, exactly, exactly. So I'm using these things that you are already familiar with from your strength of materials perspective, but if you want to get accurate enough results, because irrespective of how you do it, however you rigorous your theory is, it is an approximation. Remember, in reality, every structure is 3D, but you're treating it as 2D or 1D where it permits. And where, however rigorous it is, there is going to be a drop in accuracy. But the accuracy drop might be 0.0001%. It doesn't matter for all engineering practical purposes. You have a reasonably accurate result. But that will be possible only if you made these calculations appropriately, which is not necessarily the way, the simplistic models that we are talking about over here. There are more rigorous ways, mathematical ways, and the physics behind it is taken into account in an appropriate way so that the kind of deformations that this cross-section goes through, because remember, these are all, though I've drawn it here as fairly thick, actually you have very, very thin walled cross-sections over here. This might be a more better replica of what in reality is. So when this is undergoing certain loads, it may no longer remain in this particular shape and size. Its shape and size will change. In the simplest case, if you take a rod and apply a tensile load, you know that there's a Poisson's effect because of which there's going to be a contraction over here. And you know, in a non-circular cross-section like this, when you apply a torque, there is going to be what is known as warping, essentially your out-of-plane deformation that is going to happen. So you may not go with just this way, just the shear modulus of the material multiplied by J, the typical way that you've been calculating as IP or polar moment of inertia for this, or for any other cross-section, the typical ways in which you have been calculating. Those are all good for a first cut analysis. But there are more and more rigorous ways of calculating this. And this is just the stiffness, mind you. This stiffness is going to be one part of it. Remember, it's a dynamic problem. So there's going to be a certain level of kinetic energy also associated with it, apart from the potential energy. The potential energy is the strain energy from which all of this information is obtained. Similarly, you have a kinetic energy from which you obtain certain information in terms of the inertial behavior of this structure. So just like the material property and the geometric property went into the making of this, similarly, in terms of your mass moments of inertia, the let's say the rotational moments of inertia, you're going to have certain material and geometric properties which are going to be driving those aspects as well. So the calculation of each one of these, that is the bending stiffness, the torsional stiffness, what is known as the axial stiffness, or the couplings between them, coupling between axial and bending, coupling between axial and torsion, coupling between torsion and bending, coupling between bending in two different directions, which you might be a little familiar with, but all of these can in general be coupled with each other, and you need to get these coupling stiffnesses also in an appropriate way. So there is a very rigorous physics and math behind how you can do all of this so accurately that once it is done, that process is a little involved in terms of how you get to it, but once you've got it, when you have a structure whose let's say cross-sectional dimensions are small compared to the length, you apply this 1D model and the best of the 3D finite element analysis or commercial implementation what you have, you would see almost they are, and plot the results one on top of the other, you will get curves. You can't distinguish one curve from the other. That is the level of accuracy to which we can go. But you need that appropriate process in terms of arriving at it. This is just an approximation. What we are talking about here as the bending stiffness, or what we are talking about it as the torsional stiffness, is valid if and only if all of that warping was not there. Let's say in the torsional case, in this case it might be still okay, but once you get into problems where there is let's say a box beam like what you have over here, the inside of this rectangular box beam, or the airfoil cross section as a whole, both are closed cross sections. That's not only do you have to change your IP to, but also the GJ, what is going to happen is also going to be affected by the deformations of this out of plane as well as within the plane. Both are going to affect the way you calculate that GJ. So that stiffness is, the way you calculate is going to be affected. The inertial properties, the way you're going to get calculated is going to be affected. And therefore, the overall behavior, because those are the inputs into your 1D analysis for the reference curve. If it's a shell, those are the inputs from the, you will do a through the thickness analysis. So you will, some of you might be familiar, let's say from ISRO, who are working on composites already with so-called ABBD matrices, which are the classical laminated plate theory. Those who have not heard it, don't worry about it. But those are essentially how you calculate it is, here for a beam, you reduce the finite cross-sectional area into a point, and you talk the loci of that point to a reference curve. Here what you're going to do is to shrink. Instead of shrinking an area to a point, you're going to shrink a thickness line element into a point. And all those points that you're going to have, you're going to join them. You get, instead of a reference curve, the loci of these points is going to be a reference surface. It could be a plane for a flat structure like this. It could be a surface in a general thing.
All the points will take care of the property.
Exactly. So at those points, so if I've done this through the thickness analysis properly, I lump those properties, both the stiffness properties and the inertial properties to that particular point. So whether I do a static problem or dynamics problem, as complicated as impact or fatigue, whatever, or regular vibrational problems, whatever they may be, if I have done this calculation properly and lumped it over there, then I can treat this whole thing as a 2D problem and get almost as accurate results.
But the limitation is that it should not be wrapping.
It will not be
This wrapping.
warping. Yeah.
Warping.
Yeah.
It will not take care for that.
No, the way I've written has just E multiplied by I, and the way I calculate IYY is as an integral of Z squared dA over there. That simple models like that will give you a first cut approximation. So you will not get as accurate results as 3D finite element if you just use them. But there are more sophisticated ways of calculating this by applying the right kind of math and physics. In other words, essentially what you're doing is that the assumptions that you're making, you make them sure that those assumptions are really valid in reality, or they are almost valid in the reality case. So that once you have that kind of a situation, then yes, you would have as accurate results. Because in lumping the properties of this total line element, which is along the thickness, into a particular point, which becomes a part of the reference surface, I am taking into account all of this warping as well. So in this case, I talked about the warping. For a simple Poisson's effect, if I pull this, what is going to happen? It's going to shrink in these two directions if you have a positive Poisson's ratio material, which is most of the materials that you're going to have in the aircraft structure. So that is also, in a sense, warping. So we don't call it warping. We typically are used only to torsion of non-circular cross sections. Then we say that the plane section doesn't remain plane anymore. Some points can come out, some points can go in, different points can come out by different amounts, different points can go in to the board by different amount. So essentially, you don't have a plane anymore of the cross section, you have a surface, right? So that surface which is created is an out of plane warping that you have here. Whereas what you have here is an in-plane warping. But in reality, you have combined loads coming from everything, and you would have both the in-plane warping as well as out-of-plane warping happening simultaneously. So what we essentially mean by this term warping is a three-dimensional field. One is because it comes in the outward direction, which is along which you have the coordinate x. Just like here, you have yz, yz. For this also, the coordinate system is yz on the board. So x is going out of the board that you have over here. So yeah, z is going out of the board over here. So you're having a three-dimensional quantity. One is the warping out of plane, which is what you are used to in terms of the typical behavior under torsion of non-circular cross sections, and then the Poisson's effect kind of things that you're used to. Over and above all of this, there could be other kinds of deformation, but essentially there is a warping along x, which I can call as w sub x. There is a warping along y, I can call it wy, and wz. So essentially now it becomes a three-dimensional field, which is saying that each material point at some location yz along the cross section, at some location x along the length. So there is each material point, I can identify a particular value of x, y, z. Now that particular point can move along as an average with the whole cross section, but over and above that average motion of the cross section, each point can move with respect to the other points in the cross section by a different amount. And that difference, two adjacent points over here, can move apart, or they can move closer in the y direction. Similarly, in the z direction, two material points, if you take, they can either move together towards each other, or they can move apart from each other. So in other words, they are contributing, of course, all of their motions are contributing to the average, but they're also contributing to beyond the average because they are not all moving simultaneously by the same amount in the YZ direction, similarly in the X direction as well. There could be, if you take 2 points over here, one could move outward by a certain amount, the other could move outward by a different amount, or it could even move inside, and therefore essentially there's a relative motion that is taking place between these points. So that out of plane warping and these in plane warpings is what makes your calculation, if you just take this way and do it, or just this way and do it for the bending and torsion respectively, then you might end up with results which are not accurate enough. For example, let's say I have pulled it and this has contracted. Obviously your eye is going to reduce. So you have to take care of that into account. So similarly, out of plane motions will have their own effects. Let's not get into the details of that, because only when you see a little bit of that math, then you will understand and appreciate what actually is happening. But I think in terms of an extension of the argument, you can very clearly see that just like when there is in-plane warping, because this is within the plane of the cross-section, I call it in-plane warping, and this is happening out of the plane of the cross-section, I call it out-of-plane warping. Both put together is a three-dimensional warping field, and in general, they can affect the values of your stiffnesses in axial, bending, torsion, their coupling between each other, and also the inertial properties that you have. Because remember, like let's say the mass moment of inertia, how do you calculate it? You typically look at if it's a different materials, the density at each one of those locations multiplied by a volume element. You take small volume element dx, dy, dz, and then you see how far it is from that, and then eventually you calculate it. Very, very similar to how you calculate these products of inertia, but in the weightage function that you have there is now the mass or the density distribution. Now, similarly, when you have different materials, the different values of E at those different locations will go into picture. But all of that is fine. But once there is going to be a change in the cross-section itself, both in terms of its size as well as sometimes the shape itself can change. For example, this is flat now, this flange, it can curve slightly like this because different points are going to be moving by different amounts, it's going to curve. So not only the size of this can change, the shape of it also can slightly change. Typically, these deformations are much smaller compared to the overall deformations that the beam itself is going to undergo. For example, in the tip of a wing can go through a few feet of deformation depending upon the span that you have, but these could be of the order of a few inches or a few millimeters that you have in terms of the warping. But still, they have a huge effect on affecting this because we are going and dealing with a very complicated three-dimensional structure as either a 2D structure or a 1D structure like this. Obviously, unless and until you gather that information and accumulate it in a logical fashion using the technical competence that you have, you will end up with something that is okay in terms of a textbook like a result or just an overall qualitative understanding of how the behaviors might be. You might get very good results, but it will be far off from a practical test that you do in reality, let's say in the lab or in a flight test, or even a three-dimensional finite element analysis, or in some simple problems like this where even a 3D elasticity solution might be possible. So you could have seen some of these books like by Timoshenko, Gier, etc. in terms of the theory of elasticity. Purely elasticity-based approach, you can get to the 3D analysis results of those. But those are very rare, simple geometries for which, and simple kind of boundary conditions for which you can do that. But even for such problems, you can apply the 1D analysis, let's say in this case, you have a 3D elasticity solution for a simple kind of loading and boundary conditions. I can compare that 3D elasticity with a 1D analysis if I obtain these things in a proper way, accounting for the warp. Then they would agree almost all engineering purposes. There will be the results if I plot, let's say, the deformation versus the load, or let's say the failure limits in terms failure versus, let's say, the load that you're essentially applying. All of these information that you have, the deformations as well as the stresses that are generated, all are going to be one on top of each other, irrespective of whether you did it with 3D elasticity, 3D finite element analysis, experimental tests, flight tests, or the what we call as the dimensionally reduced models. These are essentially dimensionally reduced models because from 3D, you have reduced it to 2D. So one level of dimensional reduction has happened. This is also a dimensionally reduced problem, which is a little more complicated to get because it's going from 3D to 1D. In other words, 2 levels of dimension you have to reduce. So in other words, you're shrinking an area, which is the cross-sectional area, into a point. Whereas here, you are shrinking only a line into a point. So it's only one level of shrinking that is required over here. So to get to a plate or shell theory is very easy. But in terms of applying it, it's difficult because now you have to apply it to a reference surface. But here, to get to an accurate beam theory, to get to any ordinary beam theory is very easy. But to get to a reasonably accurate beam theory is a challenging process. But once you get it, now you're dealing with just a 1D problem. For statics, it's very simple. It's just ordinary differential equation. For dynamics, you have time also as an independent variable. Still, you'll have partial differential equations, but much easier to handle with 2 independent variables, x and t, rather than with 4 variables, x, y, z, and t, right? So that is essentially the importance of this whole process. You should understand from the point of view of needs, how we said that from the actual practical purpose of a vehicle, we are saying, yes, we need shell and beam. But now we are thinking from a structural engineer's perspective. Now that I've decided on this, I have to analyze it. What is the most efficient way of analyzing it? Yes, I can use brute force because the kind of computational power I have today, the kind of commercial software that I have available today, I can just go ahead and do a 3D analysis. But when you're doing it on a routine fashion, day in and day out, any savings that you can have, especially savings of the order of 10 or of the order of 100 that you can get by doing this, that will be amplified when you have a repetitive task, maybe for the same component or for multiple components that you're doing as a part of your whole career. Obviously, you're going to have huge benefits in terms of dealing or understanding these things. And just like the pilot has a black box into which a lot of information is recorded, similarly, this whole process of how I shrink the cross-section to a point, the end user, out of his or her own interest, might want to know. But even if he or she is not interested to know that, as long as the final results are given to them and they apply that final result properly, you're still going to get as accurate results as 3D. So it's not, though I said this is less challenging, this is more challenging, etc. Those challenges are only for people who are going to do structural engineering research. It's not for even the structural engineers who are going to just use it on an applied basis. For example, whether you use Nastran, Abacus, ANSYS, whatever, the commercial software, many of the things you don't need to go into depth in terms of how the elements are arrived at, how the element properties are arrived at, etc. From a superficial level, as long as you know how to choose an appropriate element for a particular problem, that's good enough. You don't need to go deep into the maths and physics of that. Same way over here also, when you go to dimensionally reduced problems, the process of dimensional reduction is what is somewhat challenging, especially for beams. But the end results are so easy to use because now you have just a 1D problem to deal with. So as long as you understand the end results, that is good enough. So the way we will approach this whole course is such that the end results for these will be provided to you and explained to you so that you have a clear understanding of, instead of separate compartmentalized education, you deal with axial problems separately, you deal with bending problems separately, bending in one direction and then bending in both directions. You go in a step-by-step approach, then you use torsion, etc. And at the end of the day, you realize that it's a nonlinear problem. All of these individual information is okay from a class point of view, grade point of view, but will I be able to use it in the practical situation? No. So that's the kind of education, unfortunately, I went through during my undergrad or master's, where we went through all of this routine basis, where we tried to do a lot of problems related to each one of these individually, then different kinds of open cross sections and closed cross sections, which went through torsion, what kind of warping that comes out of it. All of this information can be contained in a nutshell in an overall theory. Something like what Einstein was trying to do from a physics point of view, a unified theory for everything. He was not successful, but at least the directions in which you want to go. But here, these are much simpler problems that we are dealing with compared to the overall physics of the universe or the physics of the different materials involved, etc. So it's much simpler problem, just pure structures problem that we are dealing with. There are things that have been well validated with and regularly used by major parts of the industry, etc. So then why not take advantage of that? So
what is the order of errors we are now?
Yeah, good, very good question. Very good question. So this whole thing, remember that we are moving from 3D to a 2D model here, or 3D to 1D model here. It can be done in steps. So you can, depending upon what level of accuracy you need, you can go to build up the accuracy. So your orders of magnitude of the kind of small parameters that are associated with it, you're going to be considering. For example, in this case, we already showed that, where did I write that? Yeah, let's say this is a small parameter. T divided by R naught is a small parameter, okay? So now I can expand the results of this problem, the 3D problem, in terms of a power series of T by R naught. So depending upon what level of accuracy you need, you take only the first level or you go to the next level, etc., etc. You get, so, but for most practical purposes, you would see that if you, what we call as the, instead of starting from the first, like how in this building we call this as the first floor, we don't call the actual first floor as the first floor, we call that the ground floor, right? So ground floor, first floor. Similarly, we call it as a 0th order approximation and a first order approximation. So the 0th order approximation is essentially building you the basic minimum requirements, and that itself is fairly accurate. So if you want something that to go a little beyond that in terms of accuracy, when your actual need is, let's say damage analysis or something like that, then you have to go for a first order approximation. And it's purely from, let's say, a research perspective or to publish papers, etc., you might want to go to a second order approximation. Beyond that, for most practical problems, you don't need it at all. So from a practical engineering application point of view, all that you need is two levels. One is the so-called zeroth order approximation, which is good enough for a lot of applications, and the first order approximation. And that zeroth order approximation, what you get is exactly what you read in your textbooks. So your Euler-Bernoulli beam theories, your Saint Venant's torsion theory, or the what is called as, in the case of the plate, instead of Euler-Bernoulli, you have what is known as the Kirchhoff-Love theory. So the Kirchhoff-Love plate theory, which is a classical plate theory, and even when you go to composites, you have what is known as the extension of that classical plate theory called the classical laminated plate theory. So what you're dealing with, that particular theory is asymptotically correct in the sense that that is what I called as the ground floor, the zeroth order approximation. But when you go to the first level, what you're talking about is something better. And that is what Timoshenko tried for beams. That is what Reisner and Mindlin tried for plates and shells, but they did not do it in an accurate enough fashion, because of which you need what are known as shear correction factors, etc. So we will not do that. We will also not go through, I'll just come, we will not also go through the process of arriving at that. We will just see what are the final results that are going to be and how we can directly utilize that. There's also a course I'll be teaching in the next semester where we will go in, for those of you who are interested in structures and structural research and how we are going to shrink this into a point, how we are going to shrink this line into a point. For those people, we go into a little more detail in terms of the overall process. But for not only non-structural engineers, even many of the structural engineers regularly working in the industry, etc., that process is not important. So that course, I'm doing negative advertisement for that, but that process is not at all significant for them. But those who are keen on furthering more and more, let's say doing a PhD in structures or trying to take this to the next level for various other kind of more complex and more complex geometries and or the materials, etc., then you need to understand the overall process. Yes, please. Higher order, they do include your Timoshenko-like beam theory, or they'll include the Reisner-Mindlin plate theory, or some of them might even go for even higher order theories like the third order shear theory or third order shear and normal theory, etc., based on the deformations how you're considering. So for, let's say, thicker and thicker shells or cross sections such that it is still small compared to the length, but not very small compared to the length, what you call as short and stubby beams. So problems like that, you need to go for theories like that, and many of them are already implemented in many of the computational software. Just that the accuracy will not be as good as doing a 3D finite element in the same software if you try to do. You will see a big mismatch that is there. But many of these luckily, the same commercial software that you might be very familiar with, some of you might be familiar with, you can use user subroutines. So in this user subroutines, you can put the more accurate way of reducing this to your point. So in other words, the actual theory might take this EI along with a few corrections based on a Timoshenko theory. So instead of that, if you put it based on this more accurate theory in the user subroutine, in the same commercial software, you can go for a more accurate, better implementation, right? So, yeah.
Every component in an aircraft, every component in general, it has to be designed keeping in mind that what will be the failure criteria, how it will fail.
Correct.
What is the dominant way to fail? For example,
right.
Some component may fail in shear, some component for lateral torsional buckling. So if you try to imagine a scenario where an aircraft is going from place 1 to place 2, during its flight path it's undergoing certain maneuvers, and for that maneuver, every component in this aircraft is going a cycle of loading and unloading every time. And we are designing entire component within the elastic limit. Then why we are so concerned about the short-term effect of deflection? Because if we load it and unload it within the elastic limit, then we have to be concerned about the long-term effect like endurance and fatigue.
Correct.
So
Right.
why the short-term effects?
Right, right. Very, very excellent question. So that what you would say, what you're saying would be absolutely valid if I had, let's say, solid cross section, something like this. But once I go into thin-walled cross sections, the energy distribution between the cross-sectional energy, cross-sectional deformation energy, and the energy of the reference curves deformation, that let's say it was a straight line to start with and having some kind of a reference curve later on. So that energy and the energy associated with each cross section, the cross sectional energy has a reasonably substantial contribution towards the overall thing. Whereas when you deal with more solid cross sections like this, where B and H are of the same order of magnitude, or you deal with a tubular structure like this where T is not very small compared to R naught. It's still small compared to R naught, but not very small compared to R naught. In such situations, you can ignore those effects, and as you said, because failure is the only criteria that we are looking at, that will not be affected. But in these situations, the failure that you calculate by ignoring that will be an estimate which is very, very different from what it happens in reality, or what 3D, even a 3D computational analysis or 3D elasticity analysis, if possible, can lead to. So it's only in situations where you actually need it, you need to use it. Because anyway, your zeroth order approximation are theories that you already know from strength of materials, like your Euler-Bernoulli beam theory or Kirchhoff plate theory, classical plate theory, that still works. Okay, so what you're talking about is in situations specific to aerospace vehicles, where you have a lot of these thin-walled closed cross sections and thin-walled open cross sections, and the way they are attached, and also the materials that are used with the composite, etc. Sometimes even a solid cross section like this, once you make it out of more complicated materials in terms of the mathematical model like a composite, you might see that even in such situations you might need a more accurate result to take care of these warping measures, that is both out of plane and in plane warping. So that is the major reason why many theories are different from each other, is because they do not consider warping. But that may not be the only reason. There could be a few other reasons as well, but this is the main reason why you have a huge loss of accuracy when you go to from a 3D to a 2D model, or go from a 3D to a 1D model, even larger drop in accuracy, is because you don't consider these warping measures. Yeah. So, so even if your interest is primarily in terms of failure, in fact, there it becomes even more significant, because when you're going towards failure, not only you're having large stresses, but you're having large strains as well, or approaching strains which are close to the limit of the failure, limit of the material, right? So the strains becoming larger means that the nonlinearity in your physical distribution, that is your stress-strain relationship, will become nonlinear, and you have to take that into account. If it is a brittle material, and it's, let's say, linear elastic till the point of failure, it might be okay. But still, at the point of failure, the geometric distribution would have changed so much that you have not accounted for this warping. You essentially end up with a result that is very different from what you observe in reality. So, in fact, more than for regular analysis problems, when you are stretching the limits to understand failure and things like that, you are going to the maximum permissible strains or stresses that you have. And that's where the deformations, both global as well as these local deformations, are going to be large. And therefore, accounting for them properly becomes even more significant in a failure analysis.
So by any case, we are not going into plastic reason. We are still confined.
Right. So as far as this, what we are going to be talking in this class, we will be restricting to that. But there is a possibility that you can go beyond elastic limits also. You have to obviously take that material behavior into account. See, whether it is elastic or plastic, most of this data doesn't come from a mathematical model of the material science. There are people who work on that. It's very rigorous. But for practical purposes, all structural engineers, we just base it on tests. So we do an uniaxial test, for example. You plot the stress versus strain, you get the slope of that, then you go beyond that to the inelastic regime, you see how it behaves, and then you take that behavior into account in your model. So that's essentially how you approach. And of course, other than the strain, as we already saw, one of the primary difference between elastic and inelastic is that it starts depending on other quantities. Let's say the strain rate, for example. Okay, so the strain rate, again, it could be in different regimes. For example, the strain rate up to, let's say, a certain level, you can even consider it as static. But then you go beyond that, you have to consider it as an impact, let's say. Then you go even beyond that, very high strain rates, then you have to consider what is known as a ballistic impact, like what happens in a bomb blast and things like that. The strain rates are really, really huge. And so your material behavior, let's say plotting a stress versus strain, the curves that you get will be very, very different under these three different circumstances. So you have to take all of that data into your thing. Whatever we are saying is, suppose your 3D model is known to a certain level based on your experimental tests and the way you have post-processed that appropriately. Then from there, assuming the 3D model is reliable, can I go to a 2D model? Can I go to a 1D model? That's all that we are doing over here. But whether the 3D model itself is accurate or not, when you're going to stretch beyond elastic limits, let us say, depends on the fidelity of your tests and the test results that you get and how you have post-processed that. So you might do this whole process very accurately, but if your starting point is garbage in, garbage out is what you're going to end up with.
But we still, during case of military aircraft, we still consider the ballistic impact and other things because there is a chance of getting it.
Yes, yes. So there are certain components which are more susceptible to these, where you do need to go beyond that limit. And the same methodology will still work. See, what you need to do better now is to get a 3D model, which is, because at the 3D, it's all a material model. See, it depends only on the material rather than the geometry. Okay? It's only when you're going from the 3D to 2D or 1D, not only the material matters, but the geometries also matter. Those are all of these components. You see, there are two terms, two variables here multiplying each other. One is a material property, other is a geometric property. One is a material property, other is a geometric property. When you go to axial stiffness, you have E into A. E is a material property, A is a geometrical property. So you see that only when you're dimensionally reducing it to a beam or dimensionally reducing it to a plate or shell, both will contribute. But at the 3D level, it's a material behavior at a particular point. You're saying that when it is stressed by a certain amount, it need not be a uniaxial state of stress. It could be multi-axial state of stress. It could be shear and the normal stresses all combined together. How is it going to behave? That typically is a research area from the material science perspective. But mostly from engineering perspective, what we do is just to do tests and use the test results, post-process that and use that. So that 3D model, how you get to that, the testing process, etc., is very, very critical, because that's the starting point for us. As structural engineers, we are not getting into the depth of how to analyze that and get a model for that material behavior, let's say between molecules. There could be molecules which are just sliding apart, or molecules which are breaking, especially when you're talking about the failure. There could be certain materials, for example, certain polymers, etc. The polymer chain, how it breaks apart. At the monomer level itself, there could be something that is happening. So all of these becomes purely material science, and from actual application point of view, we really don't need all of those details. Yeah. So I think we have 12 minutes. Let me complete this slide. Any other questions on this so far? Yeah. So I think we have talked about it in already in a different sense, but essentially what we are saying is that most efficient location for the material is outwards, therefore it is a shell, but two types of shells are possible. One is what is known as an unsupported shell. That was the first transition from the truss model that you talked about. The initial aircraft were all truss-like structures, of course using fabric, but the fabric was never stressed. So the first time we talked about the skin taking the stress was when you went into so-called unsupported shells. And Typically, you use the French word monocoque to refer to that. That's what most of your textbooks and you would see research papers also referring to this. Mono, as all of you know, is single, and COQUE refers to the shell. So it's essentially referring to an egg-like shell from nature. You see that in nature, typically to protect the contents of an egg, you have a egg shell, which actually, if you analyze the egg shell material, it's a fairly low structural property material. It's not, doesn't have very high Young's modulus or failure limits, etc. But purely by the shaping of that, you are giving it a certain geometric strength so that to crush an egg is very, very difficult with just your hands. But if there is even a small imperfection that is there in the egg, then you can crush it also quite easily. But if, and many of these, one thing is, of course, the property of that from a material property perspective, it is not very great structural material. But one is the geometry. Another thing is also the fact that it has pores. It's typically porous to allow for certain transaction to take place with the environment, like the some kind of a respiration that process happens, etc. So you know that once there are pores, it's almost like a structural defect that you're talking about, though at a very small length scale that you're talking about. So already you have a material which is not very strong and stiff, and then you upon that you have these pores, makes it really something so flimsy that you think, but still it has a high crushing strength. The reason is the geometry. So that is the thing that we are talking about over here also, transmitting and resisting the load applied to the vehicle. That was indicating towards shells, and that is what nature has developed through evolution over a long period of time, and just that we are adapting that intelligently to our structures over here. So we started off with unsupported shells, and that was working fine because the aircraft that we were replacing were small aircraft flying at very low subsonic speeds, typically Mach number 0.2 or lesser. So then that seemed to be working very well, and in fact better than the truss kind of geometries that we were going for. But then as we started having greater needs in terms of the range, and therefore greater fuel to take to fly faster and to take more people along at the same time, then you had to go beyond the unsupported shell, because once you have larger vehicles and or faster vehicles, the cross-sectional size is going to become larger. For example, you want to take more payloads, obviously you can't go with the same R0. You have to increase your R0 or your length and or both, so that you accommodate more seats for them and more space for their cargo, their check-in baggage and cabin baggage, all those things. So essentially your cross-sectional size, whether it is the cross-sectional size of the shell-like structure like that, or the cross-sectional size of the interior components like the beams of the spars, etc., all of them, you need larger thing. But here we are talking still of unsupported shells, where we are not even going into these beam-like supporting or reinforcing structures. We are just saying, I want to go for this, but faster and heavier. So T starts becoming the required T in order to handle that stress levels starts becoming larger and larger. So that's what we say here. Your distributed and concentrated loads are going to be large. Why concentrated loads are going to be large? For example, larger aircraft, you need larger engines producing more thrust. They are more heavy. So the so-called concentrated loads are also going to be large. The distributed loads, of course, coming from aerodynamics. You have a heavier aircraft. Obviously, we have to generate more lift. So the lift distribution is going to be large. So the distributed as well as concentrated loads are all going to increase, and which in turn means that because when the load increases without changing anything, you're going to have bending, compressive and torsional stresses that are going to come because of the external loads in the material. That's its response. So the response also is going to be large. So these stresses are going to be large. So to avoid the stress going so close to failure or beyond the failure limit mathematically, you want to increase the thickness. That is one way of reducing the stress. So you start increasing the thickness. You can start doing that to a certain level. But beyond that, the shell thickness becomes so large that your weight penalty, the structural weight penalty, shell weight, is going to be very, very large. Once you have that, instead of going for such a thick shell, you start going for half the thickness of that shell to start with, and remove that material, as I said in the beginning of the class, and instead put it as stiffeners, and then you see that you don't need that many stiffeners, you can get rid of some of the stiffeners. So overall, you're cutting down on the amount of material that you need, and therefore the structural weight that you have to carry. So you support thinner shells by stiffening members, and those stiffening members are in the form of these spars and or stringers, etc. So those are essentially beams, your one-dimensional structures. Because so far in the whole story, we have not talked about this second half of the question. We have only been answering why shells. So this whole portion was valid till then. Now, if and only if I want to get into better performance, that is in terms of the payload range, the endurance, let's say the speed, etc., only then I need that second part of it coming into picture. But as I said, from the overall perspective, already we are talking about the wing or the tail as a cantilever, and we are talking of the fuselage as an overhung, simply supported beam. So in that sense, from an overall perspective, you already had beam-like structures based on what your aerodynamics friends have designed, because typically they were designing earlier stages for low subsonic flights. Their high aspect ratios were important. When you want to get into more and more higher speeds, like for example, you go beyond the speed of sound to supersonic, you typically have delta wings. The aspect ratio is much lower, right? So you're essentially trying to see that when you increase the performance, you are going to get more loads, and to carry those loads, the shell thickness is very large. So the 2D shell alone was not enough. You need 1D beams as well. As a combination, they can do much better. And that's what nature also learned in terms of, if you look at the bone structure in the skeleton, the way they are constructed, some of them are large bones, fairly thick. Some are thin bones, which are much longer, etc. All of that, depending on the actual functionality, the kind of loads that come under typical human life, how it is spent, these tend to evolve over a long period of time. So same thing, you had beams and frames, but actually frames were already there even in the so-called unsupported shells, because you had what are known as formers. Even in a small aircraft, you can't have only the shell. At certain locations, you spaced certain round structures which were much more rigid, made of much more rigid material compared to the skin, and therefore it retained that shape. Just that the amount of stress that they were taking was not much. It was mostly the skin itself which was taking the stress. It's a stressed skin. So in all shells, you are having a stressed skin, whether it is an unsupported shell, what we call as monocoque, or now what you're getting into, which is a semi-monocoque, which is partly monocoque is what we are essentially saying. And as he pointed out earlier, it's almost like a truss structure here. So we had like designs first, then we went to monocoque designs. Now we're trying to combine both in a certain way, but we are going to go beyond just the tensile and the compressive loads into each one of these beam-like components, taking torsion, taking bending, etc. So we are building in greater capability into those elements. So it's essentially learning from what we had done. What are the advantages? Can we retain that? What are the disadvantages? Can we try to avoid that? So you support the thinner shell by stiffening members, some of which are beams and some of which are frames. But these frames also, from a mathematical perspective, they can be thought of as made out of multiple beams which are attached to each other. For example, if you have an arch-like beam, you can think of it as two columns, and then you can think of the circular portion as another curved beam, and these are all joined to each other in some way where you have to, of course, model the way in which they are joined to each other. Or you can treat it as a single beam which is going all around, even if it's a structure like this. Let's say it's a frame within the fuselage. Now you have a frame like this. Its cross-sectional dimension is small compared to the diameter, now the circumference. So you can treat this as a beam where the boundary conditions are not like cantilever or you're simply supported you're used to. It's essentially a periodic boundary condition. So you're coming back to the same location again. So essentially at any particular location, doesn't matter where, based on your convenience, you can take that as the point where once you go by 2 pi r distance, you are coming back to the same properties, whether it is a displacement field, a stress field, everything has to match over there. So you're essentially coming to a periodic. So whether it is a closed frame or an open frame, you can treat them as beams. So whatever modeling perspective you have done already is still applicable to that, because it's taking care of these initial curvatures, it's taking care of initial twists if it is there. For example, in a helicopter rotor blade, it's very common to have a pre-twist. Even in fixed wing, you know that you typically have wash in or wash out depending upon the aerodynamic requirements. So that's also, the spar is going to be essentially a twisted beam that you're going to have. So in such, because the angle of attack you want to vary along the span of the wing, so you would have the spar also turning along with the airfoil cross section, and therefore the spar as a beam would be an initially twisted beam, what we call as a beam with a pre-twist. So pre-twist or initial curvature beams, all that is possible. So all of that modeling perspective that you derive, just two types is all that you need. One is a 2D model where it is applicable, and a 1D model where it is applicable, and then you can start applying those generic models for different structures. So once you have both shell and beam, you end up with what is known as a semi-monocoque or a partly monocoque or partly single shell kind of a structure. So the advantage, of course, is the motivation which went behind the whole thing is to reduce your structural weight, because instead of 2T, you can have with just T, and the remaining material which you shaved off, you're not using all of it as stiffeners, you're using only a part of it as stiffeners, and therefore your overall structural weight does come down. And then the other advantage of this whole process, which we didn't talk about, is in terms of the concentrated loads which are diffusing smoothly into the structure. For example, at the fuselage, some location you might have the engine attached to it. In some military aircraft, very close to the tail, you have it attached to the top of the fuselage. So those are concentrated loads that are coming. Now, if you had just the shell alone, in spite of having a fairly thick shell, you will have stress concentration, possibility of stress concentrations at those locations where the engine is attached, or even where the wing is attached to the fuselage, etc. So there is a possibility of those stress concentration. But once you bring in these beams and frames as the reinforcing supporting members, you see that you can have a large, let's say a rib, for example, at the location where the engine is going to be attached, and therefore the skin is not going to take all of that stress coming from the thrust and the weight of the engine. It's going to distribute it through the rib. Similarly, in the case of a fuselage, you would have what are known as formers, and close to locations where the wing is attached, the former cross-section will become much larger. What you would call as a bulkhead. Typically, the bulkhead word was originally used to say something which is full through the cross-section, but loosely it is used even in the aircraft industry sometimes to refer to certain formers, if they are large cross-section formers, as bulkheads. You typically have pressure bulkheads at the end, and these are ordinary bulkheads which are much heavier compared to the regular formers. So all of them will help you to diffuse the loads smoothly into the skin. In other words, the skin will not go through certain stress concentrations which it would have otherwise. Okay, so this will complete today's class. If anybody has any questions, I'll be able to answer that. Okay, then we'll meet on Monday. Thank you.